Addressing a high neutral current, specifically 78 amps, in a commercial building suggests a significant harmonic distortion problem. Correcting this involves several steps, beginning with identifying the source of the harmonics. Firstly, it's crucial to measure harmonic distortions using a power quality analyzer or a harmonic meter. These devices can quantify the harmonic content in the electrical system, providing a clear picture of the problem's severity. Secondly, trace the harmonic currents back to their source. Common sources in commercial buildings include computer rooms, with their abundant switch-mode power supplies, and heavy machinery. These devices introduce nonlinear loads that generate harmonic currents. Once the source is identified, various mitigation techniques can be employed. These techniques can be broadly categorized into passive and active methods. Passive mitigation involves using components like filters and reactors to reduce harmonic currents. One common approach is installing neutral filters on the panel where the majority of harmonic currents occur. These filters are designed to attenuate specific harmonic frequencies, reducing their impact on the system. Another passive technique involves using harmonic isolators. These devices, such as line reactors or transformers, isolate harmonic currents from the neutral conductor. Line reactors add impedance to the circuit, which reduces the flow of harmonic currents, while specially designed transformers can block the propagation of harmonics. Active mitigation, on the other hand, involves injecting compensating currents or voltages to cancel out the harmonics. Active power filters, or APs, are a prime example. These devices actively monitor the harmonic content in the system and inject negative harmonic currents that are equal in magnitude but opposite in phase to the positive harmonic currents. This effectively cancels out the harmonics, resulting in a clearer power supply. Dynamic voltage restorers, or DVRs, are another type of active mitigation device. DVR are typically installed at the service entrance to compensate for harmonic voltage distortions. They inject voltage waveforms that counteract the distortions, providing a stable and clean voltage supply to the building. Another crucial aspect of correcting high neutral current is neutral conductor upsizing. Increase the size of the neutral conductor to handle the additional harmonic currents. Harmonic currents can cause the neutral conductor to overheat, potentially leading to insulation failure and fire hazards. Therefore, it's essential to ensure that the neutral conductor is adequately sized. As a rule of thumb, ensure the neutral conductor is rated for at least 75% of the phase conductor ampacity. In some cases, especially with high harmonic loads, it may be necessary to use parallel neutral conductors to provide sufficient capacity. Furthermore, inspect and upgrade the insulation of the neutral busbar to prevent overheating and arcing. Harmonic currents can cause the neutral busbar to overheat, which can degrade the insulation and lead to arcing faults. Use busbars with high current capacity and thermal protection. This ensures that the busbar can withstand the increased current load and that any overheating is quickly detected and addressed. Improving the grounding system is another essential step. A well-designed grounding system provides a low impedance path for harmonic currents to return to their source. This reduces the voltage distortion caused by the harmonic currents and minimizes the risk of electrical shock. Install additional grounding rods or a supplemental grounding electrode. This reduces the overall impedance of the grounding system, providing a more effective path for harmonic currents. Load balancing is also an important consideration. Distribute harmonic generating loads evenly across multiple phases to reduce neutral current imbalances. When harmonic loads are concentrated on a single phase, it can result in a significant neutral current. By distributing these loads more evenly, the neutral current can be reduced. Regularly monitor harmonic levels and neutral currents to ensure the mitigation measures are effective and the system is operating safely. This involves using power quality analyzers and clamp-on ammeters to measure the harmonic content and neutral current. Perform preventative maintenance on harmonic mitigation devices and electrical equipment. This ensures that the mitigation devices are functioning properly and that the electrical equipment is not contributing to the harmonic problem. Ensure compliance with local electrical codes and safety regulations. Electrical codes often have specific requirements for harmonic mitigation and neutral conductor sizing. Compliance with these codes is essential for ensuring the safety of the electrical system. Evaluate the cost of implementing mitigation measures against the potential risks and benefits. Harmonic mitigation can be expensive, so it's important to weigh the costs against the benefits. The benefits may include reduced energy costs, improved equipment reliability, and a safer electrical system. If unsure about the best course of action, consider consulting with a qualified electrical engineer or power quality specialist for assistance. These professionals have the expertise and experience to assess the harmonic problem and recommend the most appropriate mitigation strategies. Remember that harmonic problems can vary significantly from one building to another. A thorough assessment and tailored mitigation approach are crucial for achieving effective results. It is also critical to consider applicable electrical codes, such as those published by the National Fire Protection Association in NFPA 70, otherwise known as the National Electrical Code. The NEC provides guidance on conductor sizing, overcurrent protection, grounding, and other factors relevant to managing harmonic currents. For example, NEC Section 220.61 outlines requirements for neutral conductor sizing, particularly in situations where a significant portion of the load consists of nonlinear loads. The NEC also addresses grounding and bonding requirements, which are essential for providing a low impedance path for fault currents and harmonic currents. Article 250 of the NEC provides detailed information on grounding and bonding. In addition to the NEC, IEE Standard 519, IEE Recommended Practice and Requirements for Harmonic Control in Electric Power Systems provides guidance on harmonic limits and mitigation techniques. This standard is widely used by engineers and utilities to assess and address harmonic problems. Power quality analyzers are essential tools for diagnosing harmonic problems. These devices can measure voltage and current waveforms, calculate harmonic distortion levels, and identify the sources of harmonics. Some advanced power quality analyzers can also perform transient analysis and capture waveform disturbances. When installing harmonic filters, it is important to select filters that are properly sized and tuned for the specific harmonic frequencies present in the system. Passive harmonic filters typically consist of inductors, capacitors, and resistors connected in series or parallel configurations. Active harmonic filters, on the other hand, use electronic components to inject compensating currents or voltages. When upsizing the neutral conductor, it is important to consider the ampacity of the conductor and the temperature rating of the insulation. The ampacity of a conductor is the maximum current that it can carry continuously without exceeding its temperature rating. NEC Table 310.15b16 provides ampacity ratings for conductors based on their size and insulation type. When installing grounding electrodes, it is important to ensure that they are properly connected to the grounding system. Grounding electrodes should be installed in accordance with NEC Article 250. The grounding electrode system should consist of one or more grounding electrodes, such as ground rods, ground plates, or underground metal water pipes. Load balancing involves distributing the loads evenly across the phases of the electrical system. This can be achieved by carefully planning the layout of electrical circuits and by using phase rotation to balance the loads. When monitoring harmonic levels and neutral currents, it is important to establish baseline measurements and to track changes over time. This can help to identify potential problems early and to assess the effectiveness of mitigation measures. Preventative maintenance on harmonic mitigation devices and electrical equipment should include regular inspections, cleaning, and testing. Harmonic filters should be inspected for signs of damage or deterioration. Electrical equipment should be tested to ensure that it is operating properly and is not contributing to the harmonic problem. When evaluating the cost of implementing mitigation measures, it is important to consider the long-term benefits. Harmonic mitigation can reduce energy costs, improve equipment reliability, and extend the life of electrical equipment. These benefits can often offset the initial cost of implementing mitigation measures. Consulting with a qualified electrical engineer or power quality specialist can provide valuable insights and recommendations. These professionals can perform a thorough assessment of the harmonic problem and recommend the most appropriate mitigation strategies. They can also provide guidance on electrical codes and safety regulations. To reiterate, the steps involved in addressing a high neutral current issue due to harmonics include firstly, identification of the harmonic source through measurement and tracing. Secondly, implementation of mitigation techniques such as passive filtering with neutral filters and harmonic isolators, or active filtering using active power filters and dynamic voltage restorers. Thirdly, neutral conductor upsizing to handle the increased current load, ensuring compliance with at least 75% of phase conductor ampacity. Fourthly, improving neutral busbar insulation to prevent overheating and arcing. Fifthly, enhancing the grounding system to provide a low impedance path for harmonic currents. Sixthly, load balancing to distribute harmonic generating loads evenly across phases. Seventhly, continuous monitoring and maintenance of harmonic levels and mitigation devices. Finally, adherence to electrical codes and conducting a cost-benefit analysis to justify mitigation measures. Seeking professional assistance is also advised for complex cases. These steps provide a comprehensive approach to managing and reducing high neutral current caused by harmonics in commercial buildings. Remember to prioritize safety and consult with qualified professionals to ensure effective and compliant solutions.